Welcome to my presentation. I'm Ziyue. I'm a fourth-year student studying Bachelor of Civil Engineering Honors at the University of Sydney. My thesis title is Numerical Investigation of Flexural Behavior of Geopolymer Concrete Beams. This thesis project is supervised by Professor Daniel Diaz da Costa. My topic area is numerical simulation of innovative construction material. This research topic is trying to present the implementation of finite element analysis using abacus to predict the flexural behavior of the innovative geopolymer concrete beams. The traditional matrix and reinforcement of beam is cement-based concrete and steel. You may be interested in why we try to replace them by geopolymer concrete and glass fiber reinforcement polymer, or GFRP. Fiber reinforcement polymer, or FRP, composite bars, and geopolymer concrete are promising alternatives to steel bars and traditional cement-based concrete. The non-corroding property of FRP bars make them suitable as internal reinforcement for concrete structure that are vulnerable to aggressive environment, such as marine structures and mining facilities. FRP reinforcement has high tensile strength, lightweight, non-magnetism, and high strength-to-weight ratios. Geopolymer concrete is a green material with low carbon dioxide emissions because of geopolymer binder that can be manufactured using industrial waste material. Geopolymer concrete have strength, stiffness, and other mechanical properties that are mostly superior than traditional OPC-based concrete. The combination of FRP bars and the geopolymer concrete is expected to yield a civil engineering infrastructure with high durability and sustainability. Intensive experiment work have been done as compared to numerical work by research groups on the behavior of GFRP reinforcement concrete flexural members. From the literature review, it has been observed that numerical behavior of the GFRP reinforcement flexural members in abacus is less defined, and no numerical parametric study was conducted. Therefore, to accurately simulate and analyze flexural behavior of GFRP reinforcement beam and to provide new design codes for GFRP reinforcement, a numerical parametric study is needed by examining the critical parameters that influence the flexural behavior of GFRP reinforcement beam. The geometry of finite element model was designed according to the detailed drawing shown in the upper figure. The concrete of the basements was modeled as a homogeneous three-dimensional solid. Three-dimensional wire elements was used to simulate the reinforcement. The plain concrete elastic plastic behavior was based on well-established damage plasticity mode. GFRP bars and stirrups was simulated with linear elastic material up to failure without damage characterization applied to it. The interface between the concrete and GFRP bars was not simulated because the aim of this project is to define finite element model capable to simulate the overall structural behavior of reinforcement concrete beams, but not to investigate the local response at interference between fiber reinforcement polymer and concrete. At the current stage, the numerical modes of tested beams of all 7 reinforcement layouts has been constructed in abacus. The experiment is completed in 2019 by Marana. The calibration was conducted by comparing the result of 2G, 3G in the figure, which means it has 2 GFRP bars in top and 3 GFRP bars in the bottom. The average difference between the finite element models and the experimental results was 26%. But the trend of the low deflection and low tensile strain relationship matched well. A large difference are due to noise in the simulation result, caused by setting of relatively large target time increment, which will reduce simulation time, so the simulation of each model can be completed within half an hour. More accurate and longer simulation will be conducted later to reduce noise in the results. In the next stage, the parametric study will be conducted to investigate the effect of reinforcement ratio and effect of hybrid reinforcement layouts on number of fracture cracks, fracture strengths, bending moment capacity, and degree of failure. This is the end of my presentation. Thanks for listening.